Integration techniques, lesson 5, integration by substitution. When deriving composite functions in the form of f g of x, it is possible to make the substitution u equals gx to use the chain rule. It's possible to make an appropriate substitution to rewrite the integrand as a function of a known integral. So in this case, we've got 3x take 5 to the power of 5 dx. We could write it as u to the 5 times du on 3. Or we've got sine x squared 2x dx. We could write it as sine u du. That makes those integrands a bit easier to evaluate. Several examples will illustrate this technique, which is really the chain rule in disguise. 3 common types will be explored. Case 1, requiring a simple substitution, such as the integral of 8x take 7 to the power of 6. We could let 8x take 7 equal u. In this case, 1 over 4x take 1 to the 5. We can let 4x take 1 equal u. Option 2, cases in which the substitution method is relevant where the derivative is present. See here, you've got 2x squared. The derivative of 2x squared is 4x. X cubed is 3x squared. Cos x is negative sine x, but that'll help us cancel that out. In case 3, cases where linear substitution is more appropriate, the derivative is not present. So the derivative of x is 1, which is not going to help us with that 4x. 1. Cases requiring a simple substitution. Note, this actually was covered in lesson 1. Evaluate the integral of 7x plus 11 to the power of 5 dx. Let u equals 7x plus 11. Derive du dx equals 7. Now rewrite the differential here as dx equals du on 7. The next stage is to rewrite this integrand. The integral now is written as u to the 5 du on 7 because dx is du on 7. Now you've got 1/7 of u to the 5, add 1 to the 5, which is 6, and divide by 6. So you've got 1 over 42, replace the u with 7x plus 11, to the power of 6 plus c. This step is just a repeat. It's not supposed to be there. So the answer is 1 over 42, 7x plus 11 to the 6 plus c. Example 17. Evaluate the following integrand. Let u equal 9x plus 25. Du dx equals 9. Therefore, dx equals du on 9. Step 2, rewrite the integrand. Now here, before you move on, you could rewrite this as 1. And that's 9x plus 25 all square rooted is x to the half. So to the power of a half. So if you bring that function up here to the top, to the numerator, it's going to be the function to the power of negative a half. So hence we've got 1u to the negative 1/2. Dx is du on 9. So you've got 1/9. Add 1 to negative 1/2, becomes 1/2. Divide by the 1/2. So dividing anything by a half becomes 2. So you've got 2/9 of u, which is 9x plus 25, and to the power of a half is the square root plus c. Cases number 2, cases in which the substitution method is relevant but the derivative is present. Example 18. Evaluate 4x outside of 2x squared plus 1 over 4. You let u equal 2x squared plus 1 and derive it in terms of x, du dx equals 4x. Rewrite it so it's dx equals du on 4x and proceed as we did the last example. So rewrite our integrand, which is 4x is going to remain the same, but our function here becomes u to the power of 4, and dx is replaced with du on 4x. Now we can cross out these 4x's, cancelling those out, left with u to the 4 du, which is a nice easy one to integrate. So it becomes u to the 5 over 5 plus c. Now u was 2x squared plus 1. Replace our u with 2x squared plus 1, and there's our solution. Our integral has been calculated. Example 19, sine squared theta, cos theta, d theta. So we're integrating with respect to theta. Let u equal sine theta. The benefit of doing that is that you're going to now find that du d theta is cos theta, and d theta is du over cos theta. When you rewrite your integrand, you're now going to write it as, instead of sine squared theta, it becomes u squared. Cos theta remains the same, and your d theta becomes du on cos theta. Cross out those cos thetas, you've now got an integral with respect to only u, and it's in terms of du, which is great. So add 1 to our index and divide by that number. You get 1/3 u cubed plus c. Where u was sine theta, so it's 1/3 sine cubed theta plus c. So it looks tricky, but it's actually nice logical steps involved to anti-differentiate. Three, cases where linear substitution is more appropriate. The derivative is not present. Here, let u equal 2x plus 1. Now, we're still going to find du dx, but the derivative of 2x is 2. It's not going to cancel out that x. So that means we're going to try something different. So we're going to try step 2, rewrite and derive. So here I'm going to make x the subject. So take 1 from both sides, divide by 2. Now I have an expression for x. Now, do what we did previously, which is du dx, which is 2. Rewrite it in terms of dx, which is then du over 2. Now we've got expressions for x, 2x plus 1, and dx. Let's use those to rewrite. So x was u take 1 on 2. So x here is u take 1 on 2. Our 2x plus 1 was u, so that becomes u to the 6, and dx was du on 2. Now you've only got an integrand that involves u, which is great. So let's simplify this. You've got dividing by 2 and dividing by 2, which is a quarter. Let's take that out the front. Now you've got u times u to the 6, which is u to the 7. You've got negative 1 times u to the 6, which is negative u to the 6. After following these couple of steps, you've now got a really easy integral. So now add 1 to each indice and divide by that number. So u to the 8 over 8, 6 becomes 7, divide by 7. We can now multiply each of those terms by 1/4 and replace u with 2x plus 1. So 1/4 times an eighth is going to be 1 on 32. Replace u with 2x plus 1 to the 8. And 1/4 times 1/7 is 1/28. Replace the u with 2x plus 1 to the power of 7 plus c. Tricky one, but once you get the hang of it, you'll find it really easy to do. Next one. You haven't got the derivative present. So if you let u equal x plus 1, the derivative is going to be 1, which is not going to help us with that 2x take 1 in the numerator. So rewrite. Make x the subject, which is u take 1. Step 2, part 2, is to then find the derivative. Du dx of this x is 1, hence dx equals du on 1, which is just plain old du. Substitute and then integrate. So we have our 2 lots of x. Let's replace x with u take 1. Let's replace the x plus 1 with the u. Now we only have an integrand that involves u's. So simplify this numerator. 2u is 2u. 2 times negative 1 is negative 2. Take another one is negative 3. I'd probably now divide each of those terms by u cubed. So u over u cubed is u to the negative 2. 3 over u cubed is 3u to the negative 3. Makes it easy for me to apply the power rule. Now we've got 2u to the negative 2. Take 3u to the negative 3 du. This one now is short and sweet to actually integrate. So add 1 to this becomes negative 1. So you're going to divide by negative 1. And also u to the negative 1 becomes u in the denominator. It's a positive indice. If you add 1 to negative 3, you're going to divide by negative 3. So if you add 1 to negative 3, you get negative 2. So divide by negative 2. Negative 3 on negative 2 would be 3 on 2. u to the negative 3, if you add 1, it will become u to the negative 2. It's a positive indice, it's u squared plus c. Replace u with x plus 1. So negative 2 over x plus 1, 3 over 2 lots of x plus 1 squared plus c. You can actually simplify this a bit more if you'd like. Here, to create a common denominator, I've multiplied this one by 2x plus 1, 2 outside of x plus 1. Hence, I then get a common denominator of 2 lots of x plus 1 squared. Simplifying my numerator, I get negative 4x take 1 over 2 outside of x plus 1 squared plus c. Technically, that's the integral, the antiderivative, but simplifying it's going to be a bit tidier just by creating like denominators and simplifying some algebraic expressions. Example 22. Let u equal e to the x take 1. If we make e to the x the subject, it'll help us out later. We're not going to make x the subject, otherwise you're going to start getting natural logs. We just made e to the x the subject. To derive this function here, du dx would be e to the x is e to the x, and deriving a constant is 0. So now we've got dx equals du on ex. We have expressions for all this to rewrite. So you've got e to the 3x, dx changed to du on e to the x, and e to the x take 1 was rewritten as u. Here you can cancel out e to the 3x divided by e to the x is e to the 2x. Now, think about this. Using your index laws, e to the 2x is actually e to the x all to the power of 2. Now you've got an expression for e to the x, which is u plus 1. So now we're going to write this as u plus 1 all squared over u. Now you have an integral that's in terms of du that only contains u's. So simplify your numerator, which is applying a perfect square, which is u squared plus 2u plus 1 all over u. Now each of those three terms divide by u. So you end up with u plus 2 plus u to the negative 1. Now integrate. Let's add 1 to that power. 2 will become 2u. And if you add 1 to negative 1, you're going to get 0, which is why it's ln u. So half u squared plus 2u plus ln u plus c. That's a bit trickier, but it's using the substitution method where the derivative is not present. You can rewrite this now where u was e to the x take 1. So what I've done is subbed in e to the x take 1 wherever I see a u. Hence, it's our final answer, which is our antiderivative. Another one. Rewrite this as 5x take 2 over x take 6 all squared. So x take 6 all squared is x squared take 12x plus 36. Now let u equal x take 6. Du dx is 1. Now rewrite our x here as the subject, so it becomes u plus 6. Also rewrite dx as the subject. Substitute and then integrate. So here we have 5x, so x is replaced with u plus 6. X take 6 becomes u. So x take 6 squared becomes u squared. So expand the numerator and simplify. So you have 5u plus 28 over u squared. You can now divide each of those terms by u squared. And you end up with the integral of 5 on u plus 28u to the negative 2 du. 5 over u is going to be 5 ln u. Add 1 to negative 2 will give you negative 1. Divide by negative 1 makes that 28 into negative 28. Rewrite this in terms of x. Now here, the next line, I'm going to write u to the negative 1 with a positive indice. So 5 ln x take 6, so 28 over x take 6 plus c. So that one required a little bit more intuition, but still applied the same principles as the last couple of examples. Evaluating definite integrals. In many cases, when a definite integral involves the change of variable rule, it is possible to rewrite the limits in terms of u. Example, you've got here, evaluate this integrand between 2 and 3, your limits. Now I can see x to the 5 is a function here, which the derivative of that function is 5x to the 4, which I can see the derivative present. So that u equal x to the 5. Du dx is 5x to the 4. dx equals du on 5x to the 4. Let's rewrite this integrand. Actually, we're not going to do that yet. We're going to rewrite the terminals. Now, if you know u equals x to the 5, then you can rewrite your terminals in terms of u. So I know our terminal here was 2. So if I put 2 to the power of 5, I get 32. If I have a limit or terminal of 3, and I sub that in, 3 to the 5 is 243. So what I've done now is to then, that should be step 4, rewrite this integrand in terms of our expressions here. So whenever I see an x to the 5, it's going to be sine u. My dx was du over 5x to the 4. Let's cancel out those x to the 4s. Now that instead of having 2 and 3 as my terminals, we now have 32 and 243. So now take out this 1/5. You have 1/5 the definite integral of sine u du with your terminals of 32 and 243. So evaluate sine u, the integral of that is negative cos u between 32 and 243. This means you don't have to replace u with the x to the 5 anymore because you've rewritten the terminals. So now I can sub in 243, I can sub in 32, evaluate this definite integral, and approximately equals 0.258. You don't have to do it that way. If the question says you have to rewrite it in terms of rewriting limits, then do so, but you don't necessarily have to do it. In this current step here, when you have sine u, you can replace, when you've found the definite integral, the integral, you can replace u with the x to the 5 and evaluate it. You're still going to get the same answer, which is 0.258. That's the end of integration by substitution.